Hi, in this video, we're going to have a look at transformations of the exponential function. Now, by this stage of the year, we have looked at transformations a number of times. So I'm hoping you're becoming a lot clearer with how to apply them to different functions. Remember, there are three types of transformations. There are reflections, dilations, and translations. We're going to focus for exponential functions on dilations in the direction of the y-axis, and we're going to focus on horizontal and vertical translations. I'll briefly mention reflections, but I don't think it's part of this course, so I'm only just going to mention it and move on. Similarly with dilations in the direction of the x-axis. So reflections, just remember, just means that the graph flips. So effectively, if you've got this function here and you have negative b to the power of x, then that means it's going to be b to the power of x, but made negative. And so, of course, it just flips over the x-axis like so. If you've got b to the power of negative x, then it's going to reflect this way, which means that a growth graph is going to turn into a decay graph, and a decay graph is going to turn into a growth graph. And if you think about like a to the power of negative n, what that means, that'll make sense to you. But again, I'm not spending much time on it at all, so I can move on. Dilations, I guess, is where it gets a little bit more interesting. So let me just have a look at the next page on dilations. And you've got dilations by a factor in the same direction as the x-axis or y-axis. Remember that if it's like 3x, then you've got an input dilation. And if it's like 3 times b to the power of x, then that would be an output dilation, and that would be a dilation by a factor in the same direction as the y-axis. So I've got a couple of examples to show you, but again, let's just do a quick visual so you can sort of see it. If I've got my transformations here, now this color here is going to be the base graph, and this color, oh, it's the same color, oh well, is going to be the new graph, and you can see it's all set up now so there are no transformations at all. So let's change A so that A is equal to 2. Every single point here has been stretched up. So it is a stretch that is parallel to the y-axis in the same direction as the y-axis. And that's why it looks like it is. It does kind of look the same, doesn't it? It almost looks like it's just been shifted back, but it's not what has actually happened. Every single point has been stretched up. And that means that the y-intercept has also stretched up. So that is now 2 instead of 1. If I make b a fraction, like 0.5, for example. Oops, sorry, that was a wrong thing I moved. If I make a fraction, like 0.5, then we can see that the new graph has been shrunk down from 1 to a half. Every point has been shrunk, and so we have a movement in the y direction downwards like so. Okay, so let's try and capture that and have a look at a problem, then we'll move on to translations. Like I said, there's also dilations of the x-axis, but I don't think it's in our course, so we won't touch it this year. So example 1 is y equals 3 times 2 to the power of x. Now, it could be written like this, or it could be written like this, 3 times 2 to the power of x. You'll see in your information booklet that the exponential function is written like that, a times b to the power of x plus k. So just keep that in mind. So how do we graph it? So let's look at the extreme conditions. As x goes really, really, really small, what's happening to the y value? Well, yes, we've got 3 times 2 to the power of negative 10 or 2 to the power of negative 100. But ultimately, as x gets really negative, then the fact that we're multiplying it by 3 is not doing much other than making it maybe go faster towards negative. So as x approaches negative infinity, the y coordinate is still heading towards 0. As x gets big along here, then the y coordinate is just going to get big as well. The 3 times is not really affecting it with any significance. When x equals 0, well, what does y equal? This is the bit which is worth looking at. Then y is equal to 3 times 2 to the power of 0, which is 3 times 1, which is equal to 3. So that's the change. So I can draw my graph in. I've got my asymptote already drawn in, so y equals 0. I can now draw in my line like so, and I can see that the y-intercept is now here, is now here, and it's the value when x equals 0, y equals 3. That's the y-intercept. For safety reasons, we just put in another point, and usually the point that's 1 comma something is the easiest one to work out. So when x equals 1, we've got 2 to the power of 1 is 2, 3 times 2 is equal to 6. So that's just for scale. We've got 1 comma 6. You can see that really I did not make my graph steep enough because there's no way that little distance there is 6. I probably should have gone like that a bit more. But anyway, that's why we put that point in, so it gives a reference to the person who's looking at the graph. Example 2 is y equals 0.52 to the power of 2x. Now, I didn't want to spend too much time with this. I'm not going to go through this in much detail at all, other than to show you that when I have a dilation of the x, like so, I can use that rule all the way back on page 1. This rule here, a to the power of n to the power of m is equal to a to the power of n times m. And so I'm going backwards. So n is like 2 and m is like x. I leave the x there and the 2 goes in. I'm squaring the a value. So when I do that to this problem, I get a half squared to the power of x, which is 0.25 to the power of x. So in fact, what I'm doing is if I've got a dilation of the x-axis like I have here, I can use my index rules to really just say, change the base, change the number inside, and then graph that instead. I don't think it's really covered in the course, so I just wanted to point that out, and then I'm going to move on. Translations, we've got vertical translations, as you know, and horizontal translations. Vertical translations will be affected by what we add or subtract onto 2 to the power of x, and horizontal translations will be what we add or subtract onto the x value. So when we look at example 1 here, we've got y equals 2 to the power of x minus 4. So this will have the effect of lowering the horizontal asymptote. So the first thing we can say is that the horizontal asymptote is equal to y equal to negative 4. I shouldn't put an equal sign there, should I? So the horizontal asymptote is y equals negative 4. So effectively, we kind of basically ignore that bit, and we see that bit as our new horizontal asymptote. So I'm going to fill that in with a red line, so negative 4, like so. We need to work out the y-intercept. I might do that in box 15. So the y-intercept is let x equals 0, and so we have y is equal to 2 to the power of 0 minus 4, which equals 1 minus 4, which equals negative 3. So unsurprisingly, maybe, given that we're not multiplying 2 to the power of x by anything, unsurprisingly, the y-intercept is just 1 unit above y equals minus 4. So I can pop that in there. That's minus 4 here and minus 3 here. So that's my point here. I have a look at this bit here. This is 2 to the power of x. So I know this is going to be a growth graph. It's going to go this way. And so I'm going to go like so. And that's my graph almost done. I'm missing an x-intercept. So because I've got a vertical translation which brings the graph down a bit below the x-axis, I now have an x-intercept. All my graphs until now have not had one. So I better work that out as well. So the x-intercept is when y equals 0, just like we did with polynomial functions. I'm going to squeeze it into this space here. So we've got 2 to the power of x minus 4 is equal to 0, which means that 2 to the power of x equals 4, which means that x must be equal to 2 because 2 squared equals 4. And so I can go back to my graph and label that with 2. And that will work for my one other point as well. It gives me the scale in my diagram that I need. So I'm good to go. I'm done. Example 2 has a horizontal translation. We've got 2 to the power of x plus 3. So as I draw my graph, I've got no vertical translation, which means that the horizontal asymptote is y equals 0, like so. I should be a good boy and label my axes. So there'll be no x-intercepts. I now need to work out what the graph will be in terms of growth, and I can see from this that the value is 2, which means it's going to be a growth graph, not a decay graph. If it was a half or something like that, I'd know it was a decay graph. So now I can draw my graph in. So last thing, I've got the graph in. It's a growth graph. I got interrupted, so I apologize if this is a bit disjointed. The last thing I need to do is work out what that the y-intercept is, this value here. Second last thing, actually. So I go y is equal to 2 to the power of 0 plus 3, which is 2 cubed, which is 8. So that gives us 0, 8. That tells us what that is. Like so. And then we need one other point for reference. You can be clever about this. I could use x equals 1, but that'd be 2 to the power of 4, which is 16. You could also use x equals negative 3 and go negative 3 plus 3 is 0, so 2 to the power of 0 is 1. So you can say negative 3, 1. It's really up to you. You just need a second point. Because the numbers aren't that hard, I'm going to go 2 to the power of 1 plus 3 is equal to 16. This is my one other point. And so I'm going to go 1, 16. It's not very well scaled, this graph, but I hope that kind of gives you a sense of what to do. Again, you can pick whatever your one other point is, but do one other point so that it sort of stands out. The information booklet does have this kind of information in it. You know, you got 0, a plus k, 1, ab plus k. I just find that a bit confusing personally, but maybe you're okay with it. So read this if you want to, and if it doesn't sort of make sense to you, then just use your common sense, I hope. One last one to put it all together. So if you're kind of okay with this already, maybe you can just stop the video right now if it's going on a bit too long. But I'll go through this one more example so that we can bring it all together. So we've got y is equal to 2 times 3 to the power of x plus 1 plus 5. So number one, just in our heads, we can go, yeah, this is going to be a growth graph. That's fine. And then we'll look at the rest of it. So y-intercept is when x equals 0. I'm going to do this a bit more formally this time. Let x equal 0, and so we've got y is equal to 2 multiplied by 3 to the power of 1 plus 5, which is equal to 11. So we've got 0, 11. X-intercept, do we have one? Better check first. Horizontal asymptote is y equals 5. No need to overthink it. It's just that bit there. Now, if I've got a y-intercept, a horizontal asymptote of y is equal to 5, then can I suggest to you then that we're not going to have any x-intercepts? So that's all good. Next thing I do is just pick one other value. I'm going to pick x equals minus 1. So one other point. If I had an x-intercept, that would be the one other point, but I don't. So I'm going to go one other point, and I'm going to say let x equal negative 1. So I'm going to have y is equal to 2 multiplied by 3 to the power of 1 minus 1 plus 5. So that's 2 times 3 to the power of 0 plus 5. 3 to the power of 0 is 1. So that just leaves me with 2 here, and 2 plus 5 is equal to 7. So my other point is minus 1, 7. Okay, so I've got my 2 points. I've got my shape of my graph from here. Now I'm going to put it all together really quickly. I'm going to have my y-axis and my x-axis. That was pretty good for freehand. X and y. I'm going to draw in my asymptote, which is at 5. Label your asymptote, please. Then I know it's going to go like this. I can see from my scale here at -1, I'm going to be at 7, and then and then I'm going to go through 11, and then it's going to keep on growing from then. So I think I might just make it fairly steep. So I'm going to draw my line in. Like so. So I'm now going to put in -1. Comma 7 as my one other point, and I'm going to have 0, 11 as my y-intercept, and I'm done. Have a go at doing some of the problems from the book.